Everything spins. Not as a poetic observation, as a literal, physical fact that applies to every scale at which we observe the universe. Planets spin on their axes. Moons orbit planets. Planets orbit stars. Stars orbit the centers of galaxies. Galaxies spin. Pairs of galaxies orbit each other around a common center of mass. Galaxy clusters have angular momentum. Even the cosmic filaments, the largest structures in the universe, stretching hundreds of millions of light years, show signs of rotating around their long axes. Electrons spin, or rather have a quantum property called spin that behaves like rotation in several critically important ways. Protons spin. Neutrons spin. Atomic nuclei spin. Molecules spin. Neutron stars, the remnants of exploded massive stars compressed to the size of a city, spin at rates up to 716 revolutions per second. Black holes spin, and their rotation is so fundamental to their physics that the complete mathematical description of a rotating black hole is one of the most complex exact solutions in general relativity. When you drain a bathtub, the water spirals. When you stir coffee, it circulates. When a hurricane forms, it rotates. When a tornado touches down, it is a column of spinning air. When a galaxy forms, it develops a disk structure because its constituent matter is rotating. When a star forms, it spins faster as it contracts, just as a figure skater pulls in their arms. When planets form from the disk of material surrounding a young star, they inherit the rotation of that disk. The question, why does everything in the universe spin, is one of those questions that sounds simple and is not. Not because the answer is complicated in the sense of requiring mathematics beyond ordinary comprehension, but because the answer operates at several different levels simultaneously: a mechanical level, a statistical level, a cosmological level, and a quantum mechanical level, and each level is genuinely different from the others, and each is genuinely interesting. And following the question through all of these levels reveals something fundamental about the nature of the universe that most people never encounter, despite spending their entire lives surrounded by spinning things. Tonight we are going to follow the question through all of those levels. Not to the quick answer, which exists and is correct, but which is like answering the question of why the sky is blue by saying, because of light scattering, which is accurate but leaves almost everything interesting unsaid. All the way down to what angular momentum is and why it is conserved, to why the early universe was not perfectly uniform and what that has to do with rotation, to why quantum mechanical spin is both like and profoundly unlike classical rotation, to what the maximum possible spin is for a black hole and why that limit exists, to what it would mean for the universe as a whole to be rotating and what we currently know about whether it is. Before we begin, if you put this on because the night is long and you need something to settle into, stay. What follows is worth the time. Let us start with the most fundamental concept, angular momentum, because you cannot understand why things spin without understanding what spinning actually is in the language of physics. And the language of physics reveals something about spinning that everyday experience does not. In everyday experience, spinning is obvious. A top is spinning. A wheel is spinning. The earth is spinning. The intuition for spinning is immediate and physical and correct as far as it goes. But it does not go far enough to answer the question of why everything spins. For that, you need the concept of angular momentum, the quantity that physics uses to describe rotational motion in a way that allows precise calculation and that connects spinning to the deepest symmetries of nature. Angular momentum is the rotational analogue of linear momentum. Linear momentum is mass times velocity, the quantity that describes how much motion an object has in a straight line, and that is conserved in the absence of external forces. Angular momentum is mass times velocity times the perpendicular distance from the axis of rotation, or equivalently, the moment of inertia times the angular velocity. It is the quantity that describes how much rotational motion an object has, in what direction it is rotating, and how difficult it would be to change that rotation. The direction of angular momentum deserves special attention because it is not immediately intuitive. Angular momentum is a vector. It has both a magnitude and a direction. The direction of angular momentum is perpendicular to the plane of rotation. It points along the axis around which the rotation occurs. For the Earth rotating from west to east, the angular momentum vector points toward the north celestial pole, toward Polaris, roughly speaking, out the top of the Earth's axis. For a spinning top, the angular momentum vector points along the top's axis. This directional character of angular momentum is what makes gyroscopes stable. The angular momentum vector resists being redirected, just as linear momentum resists being changed by a force. Now comes the crucial physical law. Angular momentum is conserved. In the absence of external torques, the rotational equivalent of forces, the total angular momentum of a system remains constant. This is not an empirical observation. It is a consequence of one of the deepest symmetries of nature, called rotational symmetry, or isotropy of space. The law of conservation of angular momentum follows directly, through a mathematical theorem due to Emmy Noether, from the fact that the laws of physics are the same regardless of the orientation of your coordinate system. If you perform an experiment pointing east or pointing north, the same laws apply. The physics does not have a preferred direction. This symmetry implies conservation of angular momentum, just as the symmetry of physics in time implies conservation of energy. This connection between the symmetry of space under rotation and the conservation of angular momentum is one of the most beautiful results in all of physics. It says that angular momentum is conserved not because of some specific mechanical property of objects, but because of the fundamental isotropy of space itself. As long as space has no preferred direction, angular momentum is conserved. Every spinning thing in the universe is doing so because angular momentum was imparted to it at some point, and conservation of angular momentum prevented that rotation from simply disappearing. The practical consequence of angular momentum conservation is the behavior you see in the figure skater pulling in their arms. A skater spinning with arms extended has most of their mass far from the rotation axis. Large moment of inertia, moderate angular velocity. When they pull their arms in, the moment of inertia decreases dramatically. The mass is now concentrated close to the axis. Since angular momentum equals moment of inertia times angular velocity, and angular momentum is conserved, as the moment of inertia decreases, the angular velocity must increase proportionally. The skater spins faster. No new rotation was added. The existing angular momentum was redistributed. This same phenomenon, conservation of angular momentum as a rotating system contracts, is responsible for the rotation of stars, planets, and galaxies. A slowly rotating diffuse gas cloud that contracts to form a star must spin faster as it shrinks. The angular momentum does not change, but the moment of inertia decreases dramatically. A gas cloud spanning light years that contracts to a star spanning hundreds of thousands of kilometers undergoes an enormous reduction in radius. and the angular velocity increases proportionally to the square of the radius ratio. Even a tiny initial rotation, imperceptible in the diffuse gas cloud, becomes a dramatic spin when the cloud has contracted to stellar dimensions. This explains the conservation and amplification of spin, but it does not yet explain the origin of spin. Where does the initial angular momentum come from? Why did the gas clouds that formed stars and galaxies have any angular momentum at all, rather than being perfectly non-rotating? This is the deeper question, and it requires going further back, to the early universe and to the specific physical processes that established the initial conditions for all subsequent rotation. Let us talk about what the early universe was like, and why its specific properties inevitably produced rotation. The universe, approximately 380,000 years after the Big Bang, when the cosmic microwave background radiation was emitted, was remarkably, but not perfectly, uniform. The temperature of the cosmic microwave background varies by only about 1 part in 100,000 across the sky, an extraordinarily small variation. The universe was, to an excellent approximation, homogeneous and isotropic, the same in all places and in all directions. But not perfectly. The 1 part in 100,000 temperature fluctuations represent real density fluctuations. Regions that were slightly denser and slightly hotter, and regions that were slightly less dense and slightly cooler. These fluctuations were quantum mechanical in origin. They were produced during the inflationary period in the very early universe, when quantum fluctuations in the inflaton field, the field driving inflation, were stretched to cosmic scales by the exponential expansion. Now consider what happens when you have density fluctuations in an extended medium. Any region of space that is not perfectly uniform, that has different densities in different places, will generally have some net angular momentum. This is not a law that says it must. It is a statistical statement that says it almost certainly will. A perfect sphere of uniform density has 0 angular momentum. But if the density is not exactly uniform, if some regions are denser and some are less dense, the gravitational forces between different parts of the system will in general not cancel out perfectly. There will be net torques acting between overdense and underdense regions. These torques will impart angular momentum to forming structures. This mechanism is called tidal torque theory, the theory that the rotation of galaxies is produced by gravitational tidal forces between neighbouring density fluctuations in the early universe. Before dark matter halos collapse to form galaxies, they are extended diffuse objects whose shapes are determined by the density field around them. The gravitational tidal field, the variations in gravity across the extended object, exerts a torque on this object that is determined by the misalignment between the principal axes of the object's shape and the principal axes of the tidal field. This misalignment is generally non-zero. It would be zero only in perfectly symmetric configurations, which essentially never occur in the real universe. And so a net torque is applied, and angular momentum is imparted. The angular momentum imparted through tidal torques scales with the masses and separations of the interacting structures and with the amplitude of the density fluctuations. In the early universe, when structures were small and close and the density field was nearly smooth, the tidal torques were small, but they acted over long periods, hundreds of millions of years, and the angular momentum they imparted accumulated. By the time the proto-galactic halos collapsed and stars began to form, the halos had angular momentum distributed through their mass, angular momentum that was then inherited by the galaxies and stellar systems that formed within them. This mechanism explains why galaxies rotate. It explains why the rotation of different galaxies is approximately random in direction. The specific tidal field that each proto-galactic halo experienced depended on its particular local environment and was essentially random from galaxy to galaxy. The universe has no preferred rotation axis. Rotation is a local property of each structure determined by its particular history of tidal interactions. But tidal torques are not the only mechanism contributing to rotation at galactic scales. Mergers, the collision and coalescence of smaller structures into larger ones, also contribute angular momentum. When two galaxies merge, the angular momentum of their orbit around each other is partially converted into the spin of the resulting merged galaxy. The Milky Way and Andromeda galaxies are currently approaching each other on a collision course. Their eventual merger in approximately 4.5 billion years will redistribute the angular momenta of both galaxies into the angular momentum of the resulting merged system. The interplay between tidal torques and mergers produces the observed distribution of galaxy rotation rates, characterized by the spin parameter, a dimensionless number that quantifies how fast a galaxy is rotating relative to what it would need to rotate at for centrifugal force to support it against gravity. Typical galaxies have spin parameters around 0.03 to 0.06. They are rotating at a few percent of the breakup speed. This distribution is remarkably consistent with predictions from simulations of structure formation that include tidal torques and mergers operating under the standard cosmological model. Now let us go to smaller scales and talk about why our own solar system spins the way it does. Because the specific angular momentum of the solar system has both a tidal torque origin in common with galaxies and specific local features that are worth examining in detail. The solar system formed approximately 4.6 billion years ago from a molecular cloud, a large region of gas and dust in the Milky Way. This cloud was not rotating rapidly. Its angular momentum was modest, a consequence of the tidal torques it had experienced over its history embedded in the galaxy. But when the cloud began to collapse under gravity, triggered perhaps by a nearby supernova whose shock wave compressed the gas, angular momentum conservation ensured that the collapse produced rotation. A diffuse cloud spanning perhaps a light year across, approximately 10 to the 13th meters, containing roughly 1 to 2 solar masses of material, collapsed over approximately 100,000 years to a protostellar disk of perhaps a few hundred astronomical units in radius, roughly 10 to the 13th meters in the disk. Wait, that is the same scale. The cloud collapsed to a disk whose outer edge is roughly the same radius as the cloud's initial size? Not quite. The cloud collapsed in the direction parallel to its rotation axis, becoming a disk, while the centrifugal force of the conserved angular momentum prevented collapse in the perpendicular directions. The disk radius is determined by the balance between gravity pulling inward and the angular momentum-derived centrifugal force pushing outward. The protosolar disk was a flattened, rotating structure of gas and dust, with the proto-sun forming at the center and the disk extending outward to hundreds of astronomical units. This disk, the protoplanetary disk, is the origin of all the angular momentum in the current solar system. The planets, asteroids, comets, and the Sun itself all formed from this disk, and all inherited their rotations from the rotation of the disk. This explains several specific features of the solar system's angular momentum. All the planets orbit the Sun in the same direction, counterclockwise when viewed from the north, because they all formed from the same rotating disk and inherited its rotational direction. All the planets orbit in roughly the same plane, the ecliptic, because the disk was flattened by its rotation. The Sun rotates in the same direction as the planet's orbit, again because both inherited the disk's rotation. Even most planetary moons orbit in the prograde direction, the same direction as their planets spin, because they formed from smaller disks of material that surrounded each planet during its formation. The exceptions to these rules are telling. Venus rotates retrograde, backward relative to its orbit. Uranus has a rotation axis tilted almost 90 degrees from the vertical. It essentially rotates on its side. These anomalous rotations are evidence of giant impacts in the early solar system, collisions between the young planets and large planetesimals that were massive enough to significantly alter the planet's spin. The giant impact hypothesis for the Moon's origin, the collision of a Mars-sized body with the early Earth, is another example of how large impacts can dramatically redistribute angular momentum in planetary systems. Let us now talk about the most dramatic amplification of angular momentum in astrophysics, the case of neutron stars, and specifically pulsars, because the numbers involved are some of the most extreme in nature, and they illustrate angular momentum conservation in its most spectacular form. A neutron star is what remains when a massive star, more than approximately 8 solar masses, exhausts its nuclear fuel and its core collapses. The collapse is extraordinarily rapid, from a core the size of Earth to a neutron star, perhaps 20 kilometers in diameter, in approximately a second. During this collapse, angular momentum is conserved. The pre-collapse stellar core, a sphere of compressed iron roughly the size of Earth, was rotating at some rate. The exact rate depended on the specific star, but a typical estimate is that a core of roughly 1 to 2 solar masses and radius of roughly 3,000 kilometers might be rotating with a period of a few hours to a few tens of seconds. This is a rotation rate that seems modest, comparable to the rotation of Earth. When this core collapses from a radius of 3,000 kilometers to a neutron star radius of roughly 10 kilometers, a factor of 300 in radius, the moment of inertia decreases by a factor of roughly 300 squared equals 90,000. Conservation of angular momentum then requires the angular velocity to increase by a factor of 90,000. A core spinning once every few hours becomes a neutron star spinning tens of times per second. A core spinning once per minute becomes a neutron star spinning 1,500 times per second. The most rapidly spinning pulsars known, called millisecond pulsars, spin at rates up to 716 revolutions per second. This is PSRJ 1748-2446 AD, discovered in 2004, a neutron star approximately 28,000 light-years away that completes 716 full rotations every second. Its equatorial surface, if neutron stars have a well-defined surface, moves at approximately 24% of the speed of light. The centrifugal force at the equator approaches the gravitational force that holds the star together. It is the fastest spinning object of known size in the universe. Millisecond pulsars are even more extreme than newly formed neutron stars. The initial spin of a neutron star slows over time as it radiates energy through electromagnetic emission and gravitational waves. Most ordinary pulsars, pulsars not in binary systems, are spinning at rates of a few revolutions per second or slower. Millisecond pulsars are pulsars that have been spun up, had their rotation accelerated, by accreting mass from a companion star in a binary system. As matter falls from the companion onto the neutron star, it carries angular momentum, and over millions of years this accreted angular momentum can spin the neutron star up to millisecond periods. This process, a neutron star spun up to hundreds of revolutions per second by accreted angular momentum, is sometimes called recycling. The companion star donates mass and angular momentum to the neutron star. The neutron star accumulates this angular momentum over millions of years and eventually spins at the extraordinary rates observed in millisecond pulsars. The recycled pulsars are among the most precise natural clocks known. Their rotation rates are extraordinarily stable, changing by only tiny fractions of a revolution per year, making them useful for precision timing experiments, including tests of general relativity. Now let us talk about black holes, because the spin of a black hole is simultaneously the most extreme case of rotation in astrophysics and a case where the physics becomes qualitatively different from any rotation we experience in ordinary life. When a rotating star collapses to a black hole, it carries its angular momentum with it. The angular momentum is preserved. It cannot simply disappear. A rotating black hole is described not by the simple Schwarzschild solution to Einstein's equations, which describes a non-rotating black hole, but by the Kerr solution discovered by Roy Kerr in 1963. The Kerr metric, as the mathematical description is called, contains a single additional parameter beyond the mass, the specific angular momentum or spin parameter, usually denoted A. The spin parameter A has a maximum value equal to the mass of the black hole in the natural units used in general relativity. A value of A divided by m equals 1 is called a maximally spinning or extremal black hole. A black hole with A divided by m greater than 1 cannot exist in the classical theory. It would not have an event horizon, would be a naked singularity, and violates what is called the cosmic censorship conjecture. Roger Penrose's conjecture that naked singularities cannot form in physical processes, that nature always hides singularities behind event horizons, implies that the spin of any astrophysical black hole must be at or below the extremal limit. The specific geometry of a rotating black hole is profoundly different from a non-rotating one. Around a rotating black hole, space-time itself is dragged around in the direction of rotation, an effect called frame dragging or gravitomagnetism. In the region called the ergosphere, outside the event horizon but inside a surface called the static limit, it is impossible for any object to remain stationary relative to distant observers. The rotation of the black hole drags space-time around with it, and even objects moving backward at the speed of light relative to the local frame cannot remain stationary relative to the far observer. Everything within the ergosphere is forced to co-rotate with the black hole. This frame dragging is not merely a mathematical curiosity. It has observational consequences that have been directly measured. The LIGO gravitational wave observations have measured the spins of merging black holes through the specific pattern of the gravitational waves emitted. The Event Horizon Telescope images of M87 star and Sagittarius A star, the supermassive black holes at the centers of M87 and the Milky Way, are sensitive to the spin through the shape and size of the black hole shadow and the pattern of emission in the accretion disk. Several lines of evidence suggest that many astrophysical black holes are spinning at significant fractions of the maximum, spin parameters of 0.5 to nearly 1. The Penrose process, proposed by Roger Penrose in 1969, describes a mechanism by which energy can be extracted from a rotating black hole through the ergosphere. A particle falling into the ergosphere can split into two particles, one of which falls into the event horizon with negative energy, which is allowed in the ergosphere, while the other escapes to infinity with more energy than the original particle. The net result is that energy is extracted from the rotational energy of the black hole. Theoretical calculations suggest that up to 29% of a black hole's total energy can, in principle, be extracted through this mechanism, energy that comes at the cost of slowing the black hole's spin. The Blandford-Znajek mechanism, the astrophysically relevant version of energy extraction from rotating black holes, involves magnetic fields threading the event horizon being twisted by the black hole's rotation and launching jets of material and radiation along the rotation axis. This mechanism is thought to be responsible for the relativistic jets observed emerging from the centers of active galactic nuclei and from certain X-ray binary systems. The jets extract rotational energy from the black hole and convert it into the kinetic energy of the jet. The most powerful jets known, extending for millions of light-years from their host galaxies, are powered by the rotational energy of supermassive black holes. Angular momentum conservation is at the heart of all of this. The rotating black hole has angular momentum because the material that formed it, or that fell into it during accretion, had angular momentum. That angular momentum is permanently encoded in the geometry of spacetime around the black hole. When energy is extracted through the Penrose process or the Blandford-Znajek mechanism, the black hole loses angular momentum, it slows down, but the total angular momentum of the system is conserved. Now let us talk about the quantum mechanical dimension of spin, because at the smallest scales the universe exhibits a form of rotation that is both analogous to and profoundly different from the classical rotation we have been discussing. Quantum mechanical spin is an intrinsic property of fundamental particles, an angular momentum that every particle possesses and that does not arise from any motion through space. It is not the particle spinning around its own axis in the way a top spins. The particles involved are point-like or very close to point-like, and the concept of a classical rotation does not apply. Nevertheless, spin has all the mathematical properties of angular momentum. It obeys the same commutation relations. It is conserved when there are no external torques. It combines with orbital angular momentum to give a total angular momentum that is also conserved. Every particle has a spin quantum number s that determines how much spin angular momentum it carries. The spin angular momentum is s times h bar, where h bar is the reduced Planck constant. Crucially, s can only take specific values. It is quantized. For electrons, protons, neutrons, and quarks, s equals 1/2. For photons, s equals 1. For the Higgs boson, s equals 0. For the graviton, if it exists as a fundamental particle, as general relativity implies, s equals 2. The distinction between particles with integer spin, s equals 0, 1, 2, etc., and particles with half-integer spin, s equals 1/2, 3/2, etc., is one of the most fundamental in physics. Particles with integer spin are bosons and obey Bose-Einstein statistics. Particles with half-integer spin are fermions and obey Fermi-Dirac statistics. The Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously, applies only to fermions and is a direct consequence of their half-integer spin. This principle is responsible for the stability of matter. It prevents the electrons in atoms from all collapsing into the lowest energy state, which is why atoms have the shell structure that gives rise to all of chemistry and all the diversity of matter. The spin of the electron is directly responsible for magnetism. An electron with spin is a tiny magnetic dipole. It has a north pole and a south pole, and a magnetic moment associated with its spin. In most materials, the spins of the electrons are randomly oriented, and their magnetic moments cancel out. In ferromagnetic materials, like iron, the electron spins in certain atomic orbitals spontaneously align in the same direction in regions called magnetic domains. And this alignment of electron spins is what gives iron its macroscopic magnetic properties. The permanent magnets you use every day are collections of aligned electron spins. This connection between quantum mechanical spin and macroscopic magnetism, between the intrinsic angular momentum of a fundamental particle and the magnetic properties of bulk materials, is one of the most striking examples of quantum effects manifesting at everyday scales. The refrigerator magnet is a macroscopic consequence of the spin of billions of individual electrons, all aligned in the same direction. Let us now address a specific question that often arises when thinking about universal rotation. Does the universe itself rotate? Is there a preferred axis around which the universe as a whole is spinning? This question has a definite observational answer, and the answer is no, or at least not at any level detectable by current observations. The cosmic microwave background, the most precise map we have of the large-scale structure of the early universe, shows no evidence of a preferred rotation axis. If the universe were rotating, there would be a characteristic pattern in the CMB, a spiral-like distortion, or a systematic alignment of temperature fluctuations with a preferred axis that current measurements would easily detect. No such pattern is observed. The constraints on any cosmic rotation are extraordinarily tight. The rate of any universal rotation is constrained to be less than approximately 10 to the negative 9 radians per year, meaning that even if the universe is rotating, it would complete less than one full rotation in the entire current age of the universe times approximately a billion. Any rotation that exists is so slow as to be, for all practical purposes, zero. This is consistent with the standard cosmological model, which assumes that the universe is on large scales isotropic and homogeneous, the cosmological principle. A rotating universe would break isotropy. It would have a preferred axis defined by the rotation. And the evidence from the CMB and from the distribution of galaxies strongly supports isotropy at large scales. However, the question of why the universe is not rotating, or is rotating only at such an imperceptibly slow rate, is itself interesting. The inflationary model of the early universe provides a natural explanation. Inflation, the period of exponential expansion in the very early universe, would have stretched any initial rotation of the pre-inflationary universe to scales vastly larger than the observable universe. Whatever rotation existed before inflation would be diluted by the exponential expansion until its effect on the observable universe is negligible. The observable universe that we see today is a tiny patch of a much larger universe, and the rotation of the whole would not be apparent from within this patch. But individual structures within the universe, galaxies, clusters, filaments, are rotating. Their rotation is local, produced by tidal torques and mergers acting within the observable universe, not inherited from some cosmic rotation of the universe as a whole. The rotation of local structures is consistent with a globally non-rotating universe that has angular momentum distributed locally through gravitational interactions. Let us now talk about an aspect of universal rotation that is rarely discussed in popular science: the role of angular momentum in the stability of matter itself, and specifically, why all atoms are not identical spheres. Atoms have angular momentum. The electrons in atoms occupy quantum states characterized partly by orbital angular momentum, described by the quantum numbers L and M sub L. These quantum numbers are subject to specific rules. L can be 0, 1, 2, and so on up to n-1, where n is the principal quantum number. And M sub L can range from negative L to positive L. The combination of these quantum numbers with electron spin gives each electron in an atom a specific angular momentum state. The different orbital angular momentum states, s orbitals with L equals 0, p orbitals with L equals 1, d orbitals with L equals 2, have different shapes. S orbitals are spherically symmetric. Zero angular momentum means no preferred direction. P orbitals are dumbbell-shaped. They extend along one axis. D orbitals have more complex lobed shapes. These shapes are a direct consequence of the angular momentum of the electron's quantum state. The chemistry of all elements, the periodic table, the ability of carbon to form 4 bonds in a tetrahedral arrangement, the directional character of hydrogen bonding, the magnetic properties of transition metals, all of this is a consequence of the angular momentum states that electrons occupy in atoms. Chemistry is angular momentum. The specific angular momentum quantum numbers that electrons can have, the Pauli exclusion principle that prevents multiple electrons from occupying the same state, and the specific rules governing transitions between states, these give every element its specific chemical personality. The three-dimensional structure of molecules, the geometry of bonds, the angles between them, the overall shape of the molecule, is determined by the angular momenta of the orbitals involved in the bonding. The tetrahedral geometry of methane, with hydrogen atoms at the corners of a tetrahedron around a central carbon atom, is a consequence of the specific way that the s and p orbitals of carbon combine to form hybrid orbitals. The planar geometry of benzene is a consequence of the way p orbitals, with L equals 1, oriented perpendicular to the molecular plane, overlap to form the delocalized pi system. Every molecule is shaped by angular momentum. Every chemical reaction involves the redistribution of angular momentum as bonds form and break. Every biological molecule, every protein, every DNA helix, every lipid membrane has the three-dimensional structure it has partly because of the angular momenta of the atomic orbitals involved in its chemical bonds. The double helix of DNA is literally a helical structure, a rotating geometry that arises from the specific angular momenta of the chemical bonds between nucleotides. The way proteins fold into specific three-dimensional shapes is determined by the angular momenta of the bonds in their amino acid chains. The rotation of chemical bonds, the way different parts of a molecule can rotate relative to each other around single bonds, is a fundamental aspect of molecular dynamics and biochemistry. In this sense, the reason why life exists and has the specific molecular forms it does is partly an answer to the question of why everything rotates. Angular momentum conservation, the quantization of angular momentum in atoms, and the specific angular momentum quantum numbers that electrons can have together determine the shapes of atoms and molecules, and ultimately the shapes of all biological structures. Life rotates because atoms rotate. Atoms rotate because angular momentum is quantized and conserved. Angular momentum is quantized and conserved because of the rotational symmetry of space and the quantum mechanical nature of matter. Let us now talk about something that connects the largest and smallest scales of rotation, the cosmic web and the specific pattern of angular momentum in it. The cosmic web, the large-scale structure of the universe consisting of filaments of galaxies separated by vast voids, has angular momentum distributed through it in a specific way that reflects the tidal torque mechanism. Filaments, the long, thin structures along which galaxies are preferentially located, show a tendency for galaxies within them to have their spin axes aligned parallel to the filament direction. Galaxy clusters at the intersections of filaments show a tendency for their spin axes to be perpendicular to the filaments connecting to them. This alignment of galaxy spins with the cosmic web is a prediction of the tidal torque theory. The tidal field that imparts angular momentum to protogalactic halos is correlated with the large-scale structure of the density field. Filaments have specific orientations, and the tidal field along filaments has a specific relationship to the filament direction. This correlation between the tidal field and the filament geometry produces the observed alignments of galaxy spins. The alignments are not perfect. There is substantial scatter, and the correlations are statistical rather than deterministic. But they are measurable and have been observed in surveys of galaxy properties. The measurement of these alignments, called intrinsic alignments, is important for cosmology because they represent a systematic effect that must be accounted for in weak gravitational lensing surveys. Weak lensing measures the distortion of galaxy shapes by the gravitational lensing of intervening matter. But intrinsic alignments of galaxy shapes and spins can mimic or mask the lensing signal. Understanding why galaxies have the specific angular momenta they do, and how those angular momenta are correlated with the large-scale structure of the universe, is therefore not just an academic exercise in astrophysics. It is a practical necessity for using galaxy surveys to measure cosmological parameters and test models of dark energy and dark matter. Let us talk about one more specific and remarkable aspect of rotation in the universe, the Coriolis effect and its consequences at different scales. The Coriolis effect is an apparent force that arises in rotating reference frames. In a non-rotating frame, there is no Coriolis effect. Objects move in straight lines unless acted upon by real forces. But in a rotating frame, like the surface of the Earth, an object moving in what appears to be a straight line in the non-rotating frame appears to curve in the rotating frame. This apparent curving is the Coriolis effect. On Earth, the Coriolis effect is responsible for the rotation of cyclones and anticyclones, the large weather systems that spiral around regions of low and high pressure. In the northern hemisphere, low pressure systems rotate counterclockwise, and high pressure systems rotate clockwise. In the southern hemisphere, the opposite applies. This is not because air is directly deflected by the Coriolis force. It is because the Coriolis effect determines which way air rotates as it converges toward or diverges from pressure centers. The common belief that the Coriolis effect determines which way water rotates when draining from a bathtub or sink is a myth at those scales. The Coriolis effect is real, But at the scale of a bathtub, the effect is negligibly small compared to the specific flow conditions established when the tub was filled and the orientation of the drain. You can make water drain in either direction, in either hemisphere, simply by controlling how the water was set in motion initially. The Coriolis effect only dominates at scales of hundreds of kilometers or more, at weather system scales. At planetary scales, the Coriolis effect is important for ocean circulation, for atmospheric dynamics, for the structure of jet streams, and for the general circulation patterns of planetary atmospheres. The banded structure of Jupiter's atmosphere, the alternating eastward and westward jet streams that produce the distinctive striped appearance, is partly a consequence of the Coriolis effect operating on Jupiter's rapidly rotating atmosphere. The faster a planet rotates, the more pronounced the Coriolis effect and the more strongly constrained the atmospheric circulation is by rotation. At galactic scales, the Coriolis effect is involved in the dynamics of spiral arms. The spiral arms of spiral galaxies are not material structures. They are not collections of specific stars that stay together. They are density waves, patterns of higher and lower density that move through the disk of the galaxy at a rate different from the rotation of the stars themselves. Stars passing through a spiral arm slow down as they enter the overdense region, accumulate in the arm temporarily, and then speed up as they exit. The specific shape and maintenance of spiral arms involves the Coriolis effect and the differential rotation of the galaxy, the fact that stars at different radii orbit the center at different rates. The differential rotation of the Milky Way is what winds up magnetic field lines and creates the large-scale galactic magnetic field structure. Stars and gas orbit the galactic center at approximately 220 kilometers per second at the Sun's radius. The galactic year, one complete orbit, takes approximately 225 million years. At different radii, the orbital speed, and therefore the period, differ. The inner galaxy rotates faster, and the outer galaxy rotates slower. This differential rotation stretches and amplifies magnetic field lines, contributing to the maintenance of the galactic magnetic field through a dynamo mechanism, analogous to, but different from, the dynamo that generates Earth's magnetic field. Let us go back to the beginning, to the most fundamental question: why does everything spin? The layered answer now has all its layers visible. At the deepest level, everything spins because angular momentum is conserved, and the universe began with non-zero angular momentum, or, more precisely, because the small inhomogeneities in the early universe led inevitably to non-zero angular momentum in individual structures, even if the total angular momentum of the observable universe is zero. Angular momentum is conserved because space is isotropic. It looks the same in all directions. This isotropy is not an assumption we make for convenience. It is an empirical fact confirmed by the extraordinary uniformity of the cosmic microwave background and by the distribution of galaxies across the sky. And Noether's theorem, one of the most profound results in theoretical physics, tells us that this isotropy implies conservation of angular momentum as an exact law of nature. The early universe was not perfectly uniform. The density fluctuations that seeded all subsequent structure were quantum mechanical in origin, quantum fluctuations in the inflaton field during inflation. These fluctuations ensured that no region of the universe was ever a perfectly symmetric sphere with zero angular momentum. Every region had slightly more mass in some directions than others. Every region experienced slightly different gravitational pulls from different directions. These asymmetries led inevitably to angular momentum, to rotation, in every structure that formed. As structures collapsed, as gas clouds became stars, as protogalactic halos became galaxies, angular momentum conservation ensured that the rotation became faster. The figure skater effect operates at every scale. The gas cloud spinning slowly becomes the star spinning rapidly. The rotating galaxy disk forms because the collapsing material cannot lose its angular momentum, and so it settles into a rotating disk where the centrifugal force of the rotation prevents further collapse in the plane. At quantum scales, angular momentum exists as an intrinsic property of particles, spin, that has no classical analogue, but that obeys the same conservation laws and the same mathematical structure as classical angular momentum. The quantization of spin, the Pauli exclusion principle that follows from Fermi-Dirac statistics for half-integer spin particles, and the specific angular momentum states that electrons occupy in atoms together determine the structure of all matter, the shapes of atoms, the geometries of molecules, the properties of materials, the complexity of chemistry and biology. Everything spins because the universe has no preferred direction, because quantum mechanics ensured the early universe was not perfectly uniform, because angular momentum is conserved as a consequence of the isotropy it started with, and because gravity, the dominant force on large scales, compresses rotating material into smaller volumes, causing it to spin faster. The spin you see in the figure skater, in the whirlpool, in the hurricane, in the galaxy, it is all the same physics operating at different scales on the same conserved quantity. None of it was created. All of it was inherited from the beginning and amplified by collapse. The universe spins because it was born with angular momentum it cannot lose, in a space that does not permit any preferred direction that would allow it to drain away, under the influence of a force that compresses rotating structures and therefore inevitably makes them spin faster. That is the answer at its deepest level. And the answer is beautiful, not despite its complexity, but because its complexity arises from just a few principles applied with rigorous consistency across all scales. The same conservation law that makes the figure skater spin faster when pulling in their arms makes the star spin faster as it forms from a gas cloud, makes the pulsar spin hundreds of times per second as the collapsing stellar core shrinks by a factor of thousands. The same quantum mechanical spin that gives the electron its magnetic moment gives ferromagnetic materials their macroscopic magnetism, and, ultimately, gives you the ability to stick notes to your refrigerator. It is all the same thing, rotating, conserved, inherited from the beginning, amplified by collapse, expressed at every scale in the universe, from the spin of a quark to the rotation of a galactic filament spanning hundreds of millions of light years. Everything spins because the universe has no choice. It began with angular momentum and has nowhere to put it. Let us talk about something that is rarely included in discussions of universal rotation, but that is essential for a complete picture: the specific way that angular momentum is transferred between objects, and why this transfer is not always obvious and is sometimes deeply counterintuitive. Angular momentum conservation does not mean that individual objects keep their angular momentum forever unchanged. It means that the total angular momentum of an isolated system is constant. But angular momentum can be transferred between components of the system through various mechanisms. Understanding these transfer mechanisms illuminates why the solar system looks the way it does today, why the Moon is moving away from Earth, why binary star systems evolve, and why accretion disks around black holes have the structure they do. The most familiar mechanism of angular momentum transfer is gravitational tidal interaction. Tides, the differential gravitational force across an extended body, do not just cause the rise and fall of ocean water on Earth, they transfer angular momentum between rotating bodies. Consider the Earth-Moon system. The Earth rotates once every 24 hours. The Moon orbits the Earth once every 27.3 days. Because the Earth rotates faster than the Moon orbits, the tidal bulge raised on Earth by the Moon's gravity is carried slightly ahead of the Earth-Moon line by the Earth's rotation. This displaced bulge exerts a gravitational force on the Moon that has a component in the direction of the Moon's orbital motion. It accelerates the Moon slightly. The Moon gains orbital angular momentum. By conservation of angular momentum in the Earth-Moon system, the Earth must lose angular momentum. The Earth's rotation slows down. This process is ongoing and measurable. The Earth's day is getting longer by approximately 1.7 milliseconds per century. Laser ranging measurements, bouncing laser pulses off retroreflectors left on the Moon by the Apollo missions, confirm that the Moon is receding from Earth at approximately 3.8 centimeters per year. The Moon is moving away because it is gaining angular momentum at the expense of the Earth's rotation. Projected backward in time, this means the Moon was once much closer to Earth, and the Earth rotated much faster. Approximately 620 million years ago, before the Cambrian explosion, a day on Earth was approximately 22 hours. Approximately 4 billion years ago, shortly after the Moon formed, a day may have been as short as 6 hours. The giant impact that formed the Moon left the Earth-Moon system with a very high total angular momentum and rapid rotation. Tidal interactions have been slowly redistributing that angular momentum from Earth's spin to the Moon's orbit ever since. The process will eventually reach an equilibrium. The Earth's rotation will have slowed, and the Moon will have receded until the Earth's rotation period equals the Moon's orbital period. At that point, both Earth and Moon will keep the same face toward each other, just as the Moon currently keeps the same face toward Earth. This is called a double tidal lock. The Moon is already tidally locked to Earth. It rotates once per orbit. Eventually, Earth will be tidally locked to the Moon as well. This process is called tidal braking, and it operates in every system with tidal interactions. The moons of Jupiter, Io, Europa, Ganymede and Callisto are all tidally locked to Jupiter. Most of the known moons in the solar system are tidally locked to their host planets. The planet Mercury is not fully tidally locked to the Sun, but has been braked into a specific resonance. It rotates exactly 3 times for every 2 orbits, because the Sun's tides on Mercury's slightly elliptical orbit produced this as a stable endpoint. Binary star systems show the same effects. Close binary stars, pairs of stars orbiting each other in tight orbits, are typically tidally locked, each keeping the same face toward the other. The tidal interaction has synchronized their rotation periods with their orbital periods. In binary systems where one star has evolved into a giant, expanding significantly and transferring mass to the companion, the angular momentum transferred in the mass transfer dramatically changes the orbital dynamics. Mass transferred from the inner Lagrange point carries angular momentum and can spin up the companion star significantly. This is part of how millisecond pulsars are created, as discussed earlier. Let us talk about angular momentum transfer through a completely different mechanism, magnetic braking, which is critically important in star formation and in the early evolution of stellar systems. When a gas cloud collapses to form a star, the angular momentum conservation argument suggests the star should be spinning very rapidly, as the figure skater pulls in their arms. But if you calculate how rapidly the Sun should be spinning based on the angular momentum of the cloud it formed from, the predicted spin rate is far higher than the observed spin rate. The Sun rotates once every approximately 25 days at the equator. Simple angular momentum conservation from cloud collapse predicts it should be rotating perhaps 100 times faster. Something must transfer angular momentum away from the forming star. The primary mechanism is magnetic braking. The forming star generates a magnetic field through its convective interior acting as a dynamo, and the magnetic field extends outward from the star into the surrounding disk and further into the surrounding gas. Charged particles in the disk and gas are attached to the magnetic field lines, and as the field lines rotate with the star, they drag these charged particles along. The particles at larger radii move faster than the local orbital velocity. They are coupled to the inner magnetic field, rotating faster than the local Keplerian orbital speed. And this coupling transfers angular momentum outward from the star to the surrounding material. This magnetic braking is extraordinarily efficient. Young stars, observed in star-forming regions, rotate rapidly, typically with periods of a few days. But within approximately 100 million years of reaching the main sequence, solar-type stars slow dramatically. Their rotation periods increase to weeks and then decades. The braking is done by the stellar wind, a continuous outflow of charged particles from the stellar surface. The stellar wind carries the magnetic field outward from the star, and the field lines act like a spinning rope connecting the star to the wind at large radii. The wind carries angular momentum away from the star as it flows outward. The spinning star loses angular momentum to the outflowing wind. This magnetic braking through stellar winds is what has slowed the Sun from its initial rapid rotation to its current 25-day period. The Sun is still losing angular momentum to the solar wind, very slowly, and will continue to do so. The rate of angular momentum loss depends on the strength of the magnetic field and the rate of the stellar wind, and this rate has been measured for the Sun and for other stars of similar type. The initial rapid rotation of young stars has important consequences for the formation of planetary systems. Rapidly rotating stars have stronger magnetic fields and more active stellar winds. The magnetic field in the protoplanetary disk, the disk of gas and dust from which planets form, interacts with the disk's own partially ionized gas and controls the rate at which gas spirals inward toward the star. This process, called magnetorotational instability, is one of the primary mechanisms generating the turbulence in protoplanetary disks that controls how quickly the disk evolves and how effectively angular momentum is redistributed within the disk, allowing gas to accrete onto the star. The magnetorotational instability is also the primary mechanism generating turbulence in accretion disks around compact objects, white dwarfs, neutron stars, and black holes. Without some mechanism to generate viscosity and allow angular momentum transport outward through the disk, gas falling toward a compact object would simply orbit forever. It cannot accrete because angular momentum conservation prevents it from simply falling straight in. The magnetorotational instability provides the turbulent viscosity that transfers angular momentum outward through the disk, allowing gas to spiral inward and accrete. Understanding this mechanism was one of the major theoretical advances in accretion physics in the past few decades. Let us now talk about the rotation of the Earth specifically in more detail. Because the Earth's rotation is both the most familiar case of planetary spin and one of the most carefully measured physical quantities in nature, with measurements revealing both the expected slowdown due to lunar tides and a surprising array of shorter-term fluctuations. The length of a day, the time for Earth to complete one rotation, is not constant. It varies on multiple timescales for multiple reasons. On the long timescale of hundreds of millions of years, the day is increasing. Tidal braking by the Moon is slowing Earth's rotation. This is the dominant secular trend. On timescales of years to decades, the length of day fluctuates by a few milliseconds for reasons related to the redistribution of angular momentum within the Earth system. The solid Earth, the fluid outer core, the atmosphere, and the oceans all have angular momentum, and they exchange angular momentum with each other. The atmosphere is a particularly important contributor. As air circulates in large weather patterns, jet streams, seasonal pressure systems, it carries angular momentum. When the atmosphere speeds up its rotation, the solid Earth must slow down to conserve total angular momentum. When atmospheric circulation slows, the Earth speeds up. The El Niño Southern Oscillation, the large-scale climate pattern that produces the periodic warming of the tropical Pacific, produces measurable changes in the length of day because it involves major redistributions of atmospheric angular momentum. On shorter timescales, the length of day fluctuates due to atmospheric weather systems, tidal forces from the Moon and Sun, and interactions between the fluid outer core and the solid mantle and inner core. The coupling between the outer core and the mantle, through electromagnetic interactions between the magnetic field in the core and the conducting mantle, transfers angular momentum between these two components on timescales of years to decades and produces the decade-scale fluctuations in the length of day. These measurements are made with extraordinary precision, using very long baseline interferometry, measuring the precise timing of signals from distant quasars using radio telescope arrays distributed around the world. The positions of the quasars are fixed on the sky to extremely high precision. Quasars are so distant that their proper motion is negligible, and by measuring the precise timing of their signals with multiple radio telescopes, the orientation and rotation rate of the Earth can be determined to millisecond precision. This precision monitoring of Earth's rotation is not merely an academic exercise. The GPS satellite navigation system requires accurate knowledge of Earth's orientation and rotation rate. The satellites broadcast their positions assuming a specific Earth orientation, and if the actual orientation differs from the assumed value, the calculated position of a receiver on the ground will be wrong. The corrections for Earth's variable rotation are regularly uploaded to GPS receivers to maintain accuracy. The Earth's rotation axis also precesses. It wobbles slowly around the pole of the ecliptic like a tilted spinning top precessing under gravity. This precession has a period of approximately 25,772 years, the so-called precession of the equinoxes that was known to ancient Greek astronomers. This precession is caused by the gravitational torque exerted on the Earth's equatorial bulge, the extra mass around Earth's equator, by the Moon and Sun. The torque does not change the magnitude of Earth's angular momentum, but changes its direction. The angular momentum vector traces out a cone around the ecliptic pole. This precession has profound implications for Earth's long-term climate. The direction of Earth's rotation axis determines which hemisphere receives sunlight more directly during which part of the orbit. And as the axis precesses, the relationship between the orientation of the axis and the shape of Earth's orbit changes on the 25,772-year timescale. Combined with the 100,000-year and 41,000-year cycles in Earth's orbit and axial tilt, the Milankovitch cycles, the precession of the equinoxes drives the approximately 100,000-year glacial cycles that have dominated Earth's climate for the past several million years. The ice ages come and go because Earth's rotation axis precesses. This is not a metaphor. It is a direct causal chain from the gravitational torque exerted by the Moon and Sun on Earth's equatorial bulge to the 25,772-year precession to the changing distribution of sunlight across the hemispheres through the orbit, to the accumulation or melting of ice sheets, to the transformation of global climate. The rotation of the Earth has shaped the evolution of life through the climate changes it drives. Species have evolved, adapted, migrated, and gone extinct in response to glacial cycles driven by the precession of Earth's rotation axis. The specific timing of human evolution, the spread of Homo sapiens out of Africa, the periods of innovation and adaptation that mark our species' history, occurred against the backdrop of climatic changes driven by Milankovitch cycles, in which the precession of Earth's rotation axis plays a central role. We exist in our current form partly because of the specific precession of the Earth's spin axis, and that precession exists because the Earth's rotation creates an equatorial bulge, and the Moon and Sun exert gravitational torques on that bulge. The Moon's existence, the product of the giant impact that gave the Earth-Moon system its large angular momentum, and the Sun's gravitational influence, are directly responsible for the specific precession that has driven the climate cycles that shaped our evolution. Let us now talk about something philosophically important that emerges from the full picture of universal rotation: the relationship between rotation and the arrow of time. Angular momentum is a conserved quantity. It does not have an intrinsic direction in time in the way that entropy does. The laws governing angular momentum are time symmetric. They work equally well running forward and backward in time. If you made a movie of a spinning top and ran the movie backward, the backward movie would show a top spinning in the opposite direction, and there is nothing physically impossible about a top spinning in the opposite direction. The time reversal of rotation is rotation in the opposite direction, which is perfectly physical. This is different from thermodynamic processes. If you made a movie of a glass falling off a table and shattering, and then ran it backward, you would see the shards reassembling and the glass flying back up, which is thermodynamically impossible, even though it is perfectly consistent with Newton's laws applied to individual atoms. Thermodynamic processes have a preferred time direction because entropy increases. Processes go from low entropy to high entropy states, and not the reverse. Angular momentum does not have this time asymmetry at the fundamental level, but the formation of rotating structures in the universe, the formation of galaxies, stars, and planets through gravitational collapse of initially slowly rotating gas, does have a time direction. The process goes from large, diffuse, slowly rotating gas clouds to compact, rapidly rotating objects. The reverse, compact, rapidly rotating stars spontaneously dispersing into slowly rotating diffuse gas clouds, does not happen. This time asymmetry in the formation of rotating structures is not due to angular momentum conservation, but to the thermodynamics of the collapse. Entropy increases as the gas cloud collapses and heats. So the rotation of everything in the universe is connected both to the time-symmetric law of angular momentum conservation and to the time asymmetric thermodynamic process of gravitational collapse. The two together produce the universe of rotating objects we observe. Time-symmetric rotation amplified and concentrated by time-asymmetric collapse. Let us now go somewhere that is rarely reached in discussions of rotation, the specific ways that rotation affects the perception of reality for an observer within a rotating system. We live in a rotating system. The Earth rotates. As inhabitants of the Earth's surface, we are continuously undergoing centripetal acceleration. We are being accelerated toward the Earth's axis by the centrifugal force of the rotation. At the equator, this centripetal acceleration is approximately 0.034 meters per second squared, about 0.3% of the surface gravitational acceleration. This is why the Earth is oblate. The centrifugal force causes the equatorial radius to be approximately 21 kilometers larger than the polar radius. This centripetal acceleration means that the effective surface gravity of the equator is slightly lower than at the poles. Not only is the gravitational acceleration smaller at the equator because you are further from the center of the Earth, but the centrifugal acceleration reduces the effective gravity further. The difference amounts to approximately 0.5% between equatorial and polar gravity. You weigh very slightly less at the equator than at the poles, about 0.5% less. This is a real, measurable effect. Laboratory balances can detect the difference if they are moved from low to high latitudes. The Coriolis effect of Earth's rotation also affects the trajectory of long-range projectiles, artillery shells, long-range missiles, enough that military ballistics must account for it. A shell fired due north in the northern hemisphere will curve slightly to the right due to the Coriolis effect. The further the range, the larger the deflection. At ranges of 10 kilometers, the deflection is approximately 10 meters, significant for artillery accuracy. Ocean and atmospheric circulation patterns we experience as weather and climate are profoundly shaped by the Coriolis effect of Earth's rotation. The trade winds, the persistent easterly winds that enabled the age of exploration, blow from east to west in the tropics because of the Coriolis effect. The westerlies, prevailing winds from west to east in middle latitudes, blow in the opposite direction for the same reason. The jet streams, high-altitude rivers of fast-moving air that control the movement of weather systems, are confined to specific latitude bands and flow predominantly from west to east because of the Coriolis effect. Without Earth's rotation, these circulation patterns would be completely different. The atmosphere would likely have a simpler circulation pattern, rising air near the equator, descending air near the poles, with winds flowing directly from pole to equator at the surface. The Coriolis effect breaks this simple circulation into multiple cells and creates the complex wind patterns we observe. The climate of Earth, the distribution of rainfall and temperature and wind, would be unrecognizably different on a non-rotating Earth. This means that the habitability of Earth, the specific distribution of climate zones that allow different ecosystems to develop, and ultimately the specific conditions under which human civilization emerged, is partly a consequence of Earth's rotation. The fertile river valleys of Mesopotamia and Egypt, where civilization first arose, the monsoon patterns that sustain agriculture across Asia, the trade winds that enabled European exploration, and the global exchange of goods and ideas, all of these are consequences of the rotation of the Earth interacting with solar heating and the Coriolis effect. We are not merely observing rotation from outside, we are inhabitants of a rotating system whose properties we are adapted to through billions of years of evolution. Our sense of vertical, our sense of balance, the way we move through space, all calibrated to the effective gravity of a rotating planet. The specific value of Earth's gravity, which is partly a function of its rotation, has shaped the evolution of life. Different gravity means different bone structure, different muscle mass, different cardiovascular demands, different organism sizes. The specific rotation rate of the Earth has contributed to the specific value of effective surface gravity that shaped the evolution of all terrestrial life, including us. Let us now address one of the most interesting thought experiments about rotation. What would happen if the Earth suddenly stopped rotating? This is not physically possible, but considering the consequences illuminates how deeply Earth's rotation is embedded in the conditions for life. If the Earth suddenly stopped rotating, all the angular momentum of the Earth's rotation, all the kinetic energy associated with the rotation of the solid Earth, would have to go somewhere. It would be converted to heat, the friction of everything sliding across the surface as the solid Earth decelerates, while inertia keeps everything else moving, would generate enormous amounts of heat. The atmosphere would continue moving eastward at the equatorial surface speed of approximately 1,670 km per hour, while the ground suddenly stopped. The resulting supersonic winds would be catastrophic for any surface structures. The oceans would surge. The water that is currently shaped into a slight equatorial bulge by the centrifugal force of rotation would be redistributed as the centrifugal force disappeared. The equatorial oceans would flow toward the poles as the equatorial bulge collapsed, potentially causing massive flooding of polar regions. The Earth itself would also relax. The solid Earth's equatorial bulge, maintained by centrifugal force, would slowly collapse over geological timescales as the Earth relaxed to a more spherical shape. This process would trigger massive geological activity, earthquakes and volcanic eruptions as the solid Earth readjusted. Without rotation, the day-night cycle would be replaced by a year-long day and night, one side of Earth facing the Sun for 6 months and the other side for 6 months. The temperature difference between the permanently sunlit and permanently shadowed hemispheres would be extreme, far beyond anything life as we know it could tolerate. The atmospheric circulation would be fundamentally different, driven by the extreme temperature difference between the two hemispheres rather than by the Coriolis effect of rotation. The Moon's tides would continue. The Moon would raise tides on the stationary Earth, and the friction of those tides would cause the Earth to very slowly start rotating again, this time in synchrony with the Moon's orbit. A tidally locked state where the same face of Earth always faces the Moon. The process would take billions of years. This thought experiment reveals the degree to which Earth's rotation is not merely a property of Earth, but is integrated into the entire Earth system, the shape of the planet, the dynamics of the atmosphere and oceans, the climate, the geological activity, the conditions for life. Remove the rotation, and the planet is not simply Earth rotating more slowly, it is a fundamentally different world. Let us now connect the smallest scales of rotation back to the largest, by talking about how the quantum spin of fundamental particles influences the large-scale structure of the universe. The spin of the electron, specifically the fact that electrons have spin 1/2 and are fermions obeying the Pauli exclusion principle, has consequences for the large-scale structure of the universe through the stability of atoms and the chemistry they make possible. But there is another way that quantum spin influences cosmic structure. Neutrinos, the lightest known massive particles, have spin 1/2 and are fermions. They are produced in enormous numbers in the early universe and in stellar processes. The specific spin and statistics of neutrinos affect their distribution in the universe, and through that distribution affect the growth of large-scale structure. Neutrinos move at nearly the speed of light, and their thermal motion prevents them from clustering on small scales. They smooth out density fluctuations on scales smaller than their free-streaming length. The mass of neutrinos, still not precisely measured but constrained by cosmological observations to be very small, affects the growth rate of galaxy clusters and the matter power spectrum. Gravitational waves, distortions in space-time propagating at the speed of light, are spin-2 radiation. The spin-2 nature of gravitational waves is a direct consequence of general relativity, and of the fact that gravity is described by the metric tensor, a spin-2 field. The spin-2 nature of gravitational waves means they have a specific quadrupolar polarization pattern. They stretch space in one direction while compressing it in the perpendicular direction, rather than the dipolar polarization of spin-1 electromagnetic waves. This polarization pattern is what LIGO and Virgo measure in their gravitational wave detections, the specific stretching and compression of the kilometre-scale arms of the interferometers. The spin of the inflaton field, the hypothetical scalar field driving inflation, determines many properties of the primordial fluctuations. A scalar field has spin 0. This means inflation produces primarily scalar perturbations, density fluctuations that are symmetric under rotations. It also produces a smaller amplitude of tensor perturbations, gravitational waves, whose amplitude relative to the scalar perturbations is characterized by the tensor to scalar ratio R. The specific prediction for R depends on the specific inflation model. Measurements of CMB polarization, specifically the B-mode polarization that is uniquely produced by primordial gravitational waves, can constrain R and thereby test inflationary models. The search for primordial B-mode polarization in the CMB is one of the most active frontiers in observational cosmology. If detected, at the level predicted by the simplest single-field inflation models, it would be one of the strongest confirmations of inflation and would provide direct evidence for the quantum gravitational epoch in the very early universe. The spin-2 nature of primordial gravitational waves and its signature in the polarization pattern of the CMB connects the quantum spin of the graviton to the largest observable scales in the universe. Let us talk about one more aspect of rotation that deserves attention: the stability of rotating systems, and why rotation can both create stability and lead to instability, depending on the conditions. Rotation generally provides stability against collapse. The centrifugal force of a rotating body resists gravitational compression in the plane of rotation. This is why disks are stable configurations. A rotating disk of gas or stars is supported against collapse in the plane by its rotation. Removing angular momentum from a disk allows it to collapse. Adding angular momentum prevents collapse. But rotation can also lead to instability through a different mechanism. A differentially rotating fluid, a fluid where different radii rotate at different angular velocities, is subject to the Kelvin-Helmholtz instability at the shear layers where different rotation rates meet. This instability produces turbulence and mixing at the boundaries between rotating fluid layers. In stars, the differential rotation between layers drives mixing that affects the star's chemical composition and the distribution of nuclear processed material. In accretion disks, the combination of differential rotation, The inner parts of the disk orbit faster than the outer parts following Keplerian dynamics, and the magneto-rotational instability produces the turbulence that enables accretion. The magneto-rotational instability specifically requires that the angular velocity decreases outward, which is exactly the Keplerian condition, and that a weak magnetic field threads the disk. Given these conditions, the instability grows exponentially and produces vigorous turbulence. Without this instability, gas in Keplerian orbit around a black hole would simply continue orbiting forever. The magneto-rotational instability is what allows it to accrete. The Taylor-Couette instability, the instability of rotating fluid between two coaxial cylinders rotating at different speeds, is another example of rotation-induced instability with astrophysical relevance. This instability, and its non-linear evolution into turbulent patterns, has been extensively studied in laboratory experiments, and is relevant to the dynamics of rotating neutron stars and white dwarfs, where the solid crust and the fluid interior may rotate at different rates. Rotation also plays a central role in the formation and evolution of binary star systems. When a massive star expands to become a red giant, it may fill its Roche lobe, the region within which material is gravitationally bound to it rather than to its companion. Material overflowing the Roche lobe flows toward the companion through the Lagrange point and forms an accretion disk around the companion. The angular momentum of the overflowing material, determined by the orbital angular momentum of the binary system, determines the structure of the accretion disk and the eventual fate of the mass transfer. The rates of mass transfer, the stability of the mass transfer, and the eventual outcome, whether the companion becomes a more massive star, whether novae and X-ray bursts occur, whether the system eventually produces a double neutron star or double white dwarf system that will eventually merge through gravitational wave emission, all depend critically on the angular momentum of the system and how it is redistributed during the mass transfer. Let us talk about what the specific spin of the Milky Way tells us about our galaxy's history and environment. The Milky Way is a barred spiral galaxy rotating at approximately 220 kilometers per second at the Sun's galactocentric radius of approximately 8.2 kiloparsecs. The rotation curve of the Milky Way, the orbital velocity as a function of galactocentric distance, is measured through observations of hydrogen gas, molecular clouds, and stars at different distances from the galactic center. The rotation curve is approximately flat beyond the central few kiloparsecs. Orbital velocity does not decrease with distance as it would if most of the mass were concentrated in the central bulge. This flatness is one of the primary evidences for dark matter. There must be a substantial dark matter halo extending far beyond the visible disk to produce the observed flat rotation curve. The specific angular momentum of the Milky Way, the total angular momentum of all its stars, gas, and dark matter, is a consequence of the tidal torques the protogalactic halo experienced in the early universe, combined with the angular momenta contributed by the mergers that built up the Milky Way. The Milky Way has undergone multiple mergers with smaller galaxies throughout its history. Remnants of these mergers can be identified as streams of stars in the galactic halo, moving on coherent orbits that reflect their original galaxy before it was disrupted and absorbed. The Sagittarius stream, a band of stars orbiting the Milky Way on a highly inclined orbit, is the remnant of the Sagittarius dwarf galaxy, which has been tidally disrupted by the Milky Way over the past few billion years. The Great Circle of Stars, identified in surveys of the outer Milky Way halo, reflects another past merger event. Each merger contributed angular momentum to the Milky Way's halo in a specific direction. And the distribution of angular momenta contributed by all past mergers is reflected in the kinematic structure of the stellar halo today. The Gaia satellite, launched by the European Space Agency in 2013 and having produced multiple data releases of unprecedented precision, has mapped the positions and velocities of approximately 1.8 billion stars in the Milky Way. These data have revealed the kinematic substructure of the stellar halo in unprecedented detail: streams, shells, and clouds of stars reflecting past merger events. By analyzing the angular momenta and orbital energies of these structures, it is possible to reconstruct the merger history of the Milky Way and understand how the galaxy's current spin was assembled from the angular momenta of its past constituents. This reconstruction is not merely of historical interest. The merger history of the Milky Way affected the formation of the solar system. Mergers can excite the orbits of stars and gas clouds, triggering star formation and disrupting existing planetary systems. The fact that the Sun formed approximately 4.6 billion years ago and has had a relatively stable orbit in the Milky Way since then reflects the specific merger history of our galaxy, one that was not so violent as to disrupt the formation of a stable planetary system. The rotation of the Milky Way is the rotation that made us possible, by providing the specific gravitational environment in which the Sun formed, and in which the solar system evolved to its current state over 4.6 billion years of relative stability. Everything spins: the electron in your atoms, the atoms in your molecules, the Earth beneath your feet, the Sun around which you orbit, the galaxy through which you travel. Each spinning object is a consequence of angular momentum imparted to it at some point in its history. Angular momentum that cannot be destroyed, only transferred. Each rotation is a record of the forces and torques that acted on that object in the past. Each spinning thing in the universe is a conserved echo of the conditions that gave it its spin. Conditions that ultimately trace back to the quantum fluctuations of the inflationary era, stretched to cosmic scales and translated by gravity into the spinning structures of everything we observe. Let us talk about something that connects rotation to one of the deepest open questions in physics: the problem of the origin of chirality in biological molecules, and whether the rotation of the universe, or of particles, plays any role in it. Life on Earth uses molecules with a specific handedness. Amino acids, the building blocks of proteins, are almost universally left-handed in living organisms. Sugars used in DNA and RNA are right-handed. This universality of molecular handedness is called biological homochirality, and it is one of the most puzzling facts about life on Earth. Why left-handed amino acids? Chemistry does not inherently prefer left over right. In laboratory synthesis of amino acids from simple precursors, you get equal amounts of left and right-handed forms. Why does life use one and not the other? The connection to rotation comes through a subtle quantum mechanical effect. The weak nuclear force, the force responsible for certain types of radioactive decay, violates parity symmetry. It distinguishes left from right at the most fundamental level. Electrons emitted in beta decay, a weak nuclear process, are preferentially left-handed, meaning their spin angular momentum is preferentially antiparallel to their direction of motion. This is a direct manifestation of parity violation by the weak force. This parity violation propagates subtly into the energy of chiral molecules. Left-handed and right-handed amino acids have very slightly different energies. on the order of 10 to the negative 17 electron volts, due to the parity-violating contribution of the weak force to molecular energy levels. This energy difference is extraordinarily small, far too small to be measured directly with current technology, and far too small to drive the observed homochirality by thermodynamic selection at room temperature. Whether this tiny energy difference could have amplified over billions of years of chemical evolution to produce biological homochirality is an open question. Several mechanisms have been proposed, including the possibility that polarized light from rotating neutron stars or other astrophysical sources preferentially degraded one-handedness of prebiotic molecules in space, leaving the surviving molecules enriched in one-handedness. The connection to rotation here is through the circular polarization of light emitted by rotating magnetized neutron stars. The spin of these extreme objects producing circularly polarized radiation that could differentially affect chiral molecules. None of these mechanisms has been definitively established. The origin of biological homochirality remains one of the genuine open questions in the origin of life field. But the fact that the question connects to the rotation of neutron stars, to the parity-violating weak force, and to the spin-angular momentum of electrons illustrates how deeply rotation is embedded in the physics of the universe at every level, including levels relevant to the specific chemistry of life. Let us now talk about the specific physics of why spiral galaxies have spiral arms, because the spiral structure of galaxies is one of the most visually striking consequences of rotation, and the physics underlying it is genuinely surprising and different from what most people assume. When you look at a photograph of a spiral galaxy, the Andromeda Galaxy, the Whirlpool Galaxy, our own Milky Way reconstructed from survey data, the spiral arms appear to be material structures, like the arms of a pinwheel, rotating rigidly with the galaxy. This intuition is wrong. The spiral arms are not material structures, they are waves. The reason material spiral arms cannot persist is differential rotation. Stars at different radii in a galaxy orbit the center at different periods. The inner stars orbit faster than the outer stars. If spiral arms were material, fixed collections of specific stars, they would be wound up by this differential rotation in a few galactic orbits. Within a billion years or so, the arms would have wound so tightly they would be invisible. But spiral galaxies, billions of years old, still have open, prominent spiral arms. This is called the winding problem. The resolution of the winding problem is the density wave theory developed by C.C. Lin and Frank Hsu in the 1960s. In this theory, the spiral arms are long-lived density waves, patterns of slightly enhanced density that move through the disk at a specific pattern speed, different from the rotation speed of the stars and gas. Stars and gas pass through the spiral arms as they orbit the galaxy, slowing down as they enter the denser arm, spending more time in the arm, and then speeding up as they exit. The arm is always denser than the surrounding disk, but it is made of different stars at different times. The analogy is with a traffic jam on a highway. The jam, the dense cluster of slow-moving cars, can persist for hours at a specific location, even though individual cars are constantly flowing through it. The jam is a density wave in the traffic, not a fixed collection of specific cars. Similarly, the spiral arm is a density wave in the stellar disk, not a fixed collection of specific stars. The star formation that makes spiral arms visible, young, bright blue stars, ionized hydrogen nebulae, is triggered by the compression of gas as it enters the spiral arm's density wave. Gas clouds entering the overdense arm are compressed and cooled, crossing the threshold for gravitational collapse and triggering star formation. The bright young stars that form illuminate the arm and make it visible, even though the arm itself is a wave rather than a physical structure. The pattern speed of the density wave, the rate at which the spiral pattern rotates, is generally less than the rotation speed of the stars at the Sun's galactic radius. There is a specific radius called the co-rotation radius, where the pattern speed and the stellar orbital speed are equal, where the stars orbit in sync with the spiral pattern. Inside the co-rotation radius, stars orbit faster than the pattern, and so they catch up to the spiral arms. Outside the co-rotation radius, stars orbit slower than the pattern, and so the pattern overtakes them. The Sun is located near, but not exactly at, the co-rotation radius of the Milky Way. This location, near co-rotation, may be significant. Stars near the co-rotation radius spend more time in the vicinity of the spiral arms and are therefore more frequently subject to the perturbations of the arm's density wave. The suggestion has been made that the Sun's location near co-rotation is not coincidental, that the stability of our solar system over billions of years and the particular conditions that allowed life to develop may reflect, in part, the specific location of the Sun relative to the Milky Way's spiral structure. There is a related structure called the galactic bar, the central bar-shaped concentration of stars that crosses the central bulge of the Milky Way. The bar rotates rigidly, unlike the disk, where different radii rotate at different speeds. The bar rotates as a solid body because it is a coherent gravitational structure. The bar's rotation rate is characterized by its pattern speed, and the radius at which the bar's pattern speed equals the local circular velocity, the corrotation radius of the bar, is an important dynamical parameter of the Milky Way. The interaction between the bar and the disk produces resonances, orbital resonances, between the orbital period of stars in the disk and the rotation period of the bar. At these resonances, the bar exerts systematic gravitational torques on the stars that can pump energy and angular momentum into stellar orbits, producing families of orbits with specific kinematic signatures. The Hercules stream, a kinematically distinct group of stars in the solar neighborhood that includes the Sun's nearby stellar environment, is thought to be associated with an orbital resonance with the galactic bar. Understanding the bar's angular velocity and the location of its resonances is important for understanding the dynamical history of the solar neighborhood. Let us now talk about what happens to rotation at the very end of stellar evolution. Specifically, what happens to the angular momentum of a star as it dies, and how the angular momentum of the remnant is related to the angular momentum of the progenitor. When a low to intermediate mass star, from roughly 0.8 to 8 solar masses, exhausts its core hydrogen and eventually helium, it expels its outer layers as a planetary nebula and leaves behind a white dwarf. The white dwarf retains the angular momentum of the stellar core at the time of the expulsion, but the expulsion itself redistributes angular momentum. The shells of the planetary nebula carry angular momentum as they expand, leaving the white dwarf with a specific angular momentum that depends on the details of the mass loss process. Most observed white dwarfs rotate slowly, with periods of hours to days. This is significantly slower than might be expected if angular momentum was simply conserved from the main sequence star. The slow rotation of white dwarfs implies that significant angular momentum was lost during the asymptotic giant branch phase, the period of heavy mass loss preceding the planetary nebula stage. The details of this angular momentum loss, through stellar winds, through the interaction of pulsations with the outer envelope, through the possible presence of a binary companion, are not fully understood and are an active area of stellar evolution research. Some white dwarfs rotate rapidly, periods of minutes or even seconds. These are likely either the products of stellar mergers, where the merger produced a rapidly spinning remnant, or white dwarfs that have been spun up by accretion from a companion star. The rapidly rotating white dwarfs from mergers are of particular interest because they may be the progenitors of Type 1a supernovae, the thermonuclear explosions of white dwarfs that have been used as standard candles for measuring the expansion history of the universe and for establishing the existence of dark energy. The angular momentum of the merged white dwarf remnant and how it is subsequently redistributed through the expanding white dwarf as it accretes mass up to or beyond the Chandrasekhar mass limit is an important parameter in models of Type 1a supernova explosions. The specific angular momentum affects the density and temperature structure of the exploding white dwarf, and through that, the brightness and color of the resulting supernova. Systematic effects from white dwarf angular momentum could, in principle, bias the cosmological measurements that use Type 1a supernovae as standard candles. If rapidly rotating white dwarfs explode differently from slowly rotating ones, the inferred distances could be systematically wrong. This connection, from the angular momentum of a white dwarf remnant to the calibration of cosmic distances to the measurement of dark energy, illustrates once again how rotation at one scale has consequences at completely different scales. Let us now talk about some of the most recent observational developments in our understanding of angular momentum and rotation in the universe, results that have come from large astronomical surveys and from the LIGO Gravitational Wave Observatory in the past few years. The LIGO and Virgo gravitational wave observatories have measured the spins of approximately 90 pairs of merging black holes as of the most recent observational catalogue. These measurements provide a direct probe of the angular momentum of stellar mass black holes in binary systems, objects that cannot be observed through electromagnetic radiation. The distribution of black hole spins measured by LIGO and Virgo has revealed several interesting features. First, the spins of black holes in merging binary systems are typically low. The effective spin parameter of most systems is small, meaning the black hole's spins are not strongly aligned with the orbital angular momentum. This is different from what would be expected if the two black holes formed from massive stars that were both rotating rapidly and whose spin axes were aligned with the orbital axis. The low effective spins suggest either that the black holes formed with low spins, perhaps massive stars that lost most of their angular momentum in stellar winds before collapsing, or that the binary system evolved through a mechanism such as dynamical capture of two black holes in a dense cluster, that does not align the spins with the orbit. Second, there are intriguing hints, not yet statistically confirmed, of events where the effective spin is negative, meaning one or both black holes are spinning backward relative to the orbital direction. This would be strong evidence for dynamical formation in dense stellar clusters, rather than isolated binary star formation, since only dynamical processes can produce retrograde spins relative to the orbital angular momentum. Third, the masses and spins of the black holes, measured by LIGO and Virgo, are now being used to test the properties of black holes as predicted by general relativity. Kerr black holes. The specific solution describing rotating black holes have a maximum spin that is exactly equal to the mass in natural units. The no-hair theorem of general relativity states that a black hole is completely characterized by its mass and spin and charge, nothing else. Deviations from Kerr behavior would be signatures of new physics beyond general relativity. Current measurements are consistent with the Kerr prediction, but the statistical power is limited. Future observations with the expanded LIGO network and with the planned space-based gravitational wave observatory LISA will provide much stronger tests. The Euclid satellite, launched in 2023, is conducting a survey of approximately 1.5 billion galaxies, designed to measure the shapes, positions, and orientations of galaxies across a substantial fraction of the sky. Among its primary science goals is the measurement of weak gravitational lensing, the subtle distortion of galaxy shapes by the gravitational lensing of intervening matter. But the Euclid data also contains information about the intrinsic shapes and spin axes of galaxies, the intrinsic alignments discussed earlier. The Euclid intrinsic alignment measurements will constrain the tidal torque mechanism that imparts angular momentum to galaxies. By measuring how galaxy spin axes are correlated with each other and with the large-scale structure of the cosmic web, the data will test specific predictions of tidal torque theory and its more modern extensions. These measurements will also be necessary to isolate the pure lensing signal from the intrinsic alignment contamination, a systematic effect that, if not properly accounted for, would bias the cosmological measurements. The Roman Space Telescope, planned for launch later in the 2020s, will complement Euclid with a wide-field infrared survey designed to measure galaxy shapes and positions over an even larger volume of the universe. The combined data from Euclid and Roman will give the most precise measurements of the large-scale distribution of angular momentum in the universe ever obtained, constraining models of how angular momentum is distributed in the cosmic web and how it flows between different structures as they evolve. The Square Kilometre Array, the large radio telescope under construction in South Africa and Australia, will measure the rotation of hydrogen gas in millions of galaxies through the 21-centimetre hydrogen emission line. The Doppler shift of this line, as the gas on different sides of a galaxy moves toward or away from us, traces the rotation curve of the galaxy, the orbital velocity as a function of radius. For enormous samples of galaxies, the SKA will be able to study the distribution of galaxy spin parameters, the alignment of galaxy spins with the cosmic web, and the variation of rotation curves with galaxy properties and environment, with unprecedented statistical precision. These upcoming surveys will transform our empirical understanding of angular momentum in the universe, providing datasets large enough to test theoretical models with statistical power that current surveys cannot approach, and to discover correlations and patterns in the distribution of rotation that current observations cannot detect. Let us talk about one more aspect of rotation that has not yet been addressed: the role of rotation in the physics of black hole mergers, and why the specific spins of the merging black holes matter for the gravitational waves produced. When two black holes spiral together and merge, the gravitational waves they produce encode information about the masses and spins of the merging objects. The spin of each black hole affects the orbital evolution through a phenomenon called spin-orbit coupling, the interaction between the spin angular momenta of the black holes and the orbital angular momentum of the binary. Spin-orbit coupling causes the orbital plane to precess, to slowly change orientation as the binary evolves. This precession produces a characteristic modulation of the gravitational wave signal called precession of the orbital plane, or spin precession. Detecting and measuring this spin precession in LIGO data allows the individual spins of the two black holes to be measured, their magnitudes and their orientations relative to the orbital plane. This is what provides the information about effective spin parameters and the distribution of spin orientations discussed earlier. The richer the LIGO data, the higher the signal-to-noise ratio, the more precisely the spin parameters can be extracted. When the two black holes merge, they form a single remnant black hole that is initially highly distorted, ringing like a struck bell in what is called the ring-down phase. The ring-down produces gravitational waves at specific frequencies, the quasi-normal modes, that are determined entirely by the mass and spin of the remnant black hole. By measuring the ring-down frequencies, the mass and spin of the remnant can be determined. This is a direct test of the no-hair theorem. If the remnant is a Kerr black hole, as general relativity predicts, its ring-down must be described by the Kerr quasi-normal mode spectrum. Current LIGO observations have confirmed the ring-down is consistent with Kerr black holes for the events with sufficient signal-to-noise ratio. But the tests are still limited by the signal quality. The ring-down signal is shorter and weaker than the in-spiral signal that precedes it. Future gravitational wave detectors, the Einstein telescope and Cosmic Explorer planned for the 2030s, will have dramatically improved sensitivity and will detect black hole mergers at much higher signal-to-noise ratio. These instruments will allow precision tests of the Kerr metric in the ring-down phase at a level that could detect subtle deviations from Kerr behavior if they exist. The merging black hole, after the ring-down, settles into a final Kerr state. The mass and spin of this final state are determined by conservation of energy and angular momentum. The total energy and angular momentum of the system must be conserved, with the energy radiated in gravitational waves subtracted from the initial total. For typical black hole mergers, the gravitational wave emission carries away approximately 5% of the total energy and a significant fraction of the angular momentum. The final spin of the remnant is reduced from what angular momentum conservation of the individual spins and orbital angular momentum would give, because angular momentum was radiated away. For the most extreme cases, equal mass black holes each spinning maximally in the same direction as the orbit, numerical relativity simulations predict that the final spin of the remnant can approach the maximum Kerr spin, A equals m. Whether any observed LIGO event has produced a near-extremal Kerr black hole is an active area of analysis. The answer has implications both for understanding black hole formation and evolution, and for testing the specific predictions of general relativity at the extreme spin limit. Let us bring together all of the threads we have examined and see how they form a single coherent picture of rotation in the universe. Not as a collection of separate phenomena at different scales, but as expressions of a single underlying physical reality. At the deepest level, angular momentum is a conserved quantity that follows from the rotational symmetry of space, from the fact that the laws of physics are the same regardless of orientation. This symmetry is one of the foundational facts about the universe, and the conservation of angular momentum it implies operates at every scale without exception. Nothing that spins can stop spinning without transferring its angular momentum somewhere else. Nothing that is stationary can start spinning without receiving angular momentum from somewhere. The total angular momentum of any isolated system is fixed and eternal. From this foundation, everything else follows. The early universe had small but non-zero density fluctuations with small but non-zero angular momenta, a direct consequence of the inhomogeneity required by quantum mechanics operating during inflation. These fluctuations grew under gravity and were given angular momentum by tidal interactions, the gravitational pulls of neighbouring overdensities producing torques that imparted rotation. As structures collapsed, angular momentum conservation caused them to spin faster, diffuse clouds becoming compact rotating objects, whether stars, galaxies, or neutron stars. Compact objects retain their angular momentum and spin, essentially forever, or until tidal interactions, gravitational waves, or other mechanisms slowly transfer it away. At quantum scales, angular momentum is quantized. Particles have intrinsic spin that is half-integer or integer multiples of the fundamental quantum of action. The statistics associated with this spin, bosonic or fermionic, determine the structure of matter at every level, from atomic orbitals to macroscopic materials. The magnetism of materials is a macroscopic expression of quantum spin. The stability of matter against collapse is enforced by the Pauli exclusion principle, which follows from Fermi-Dirac statistics, which follows from half-integer spin. The specific shapes of atomic orbitals and molecular structures that make chemistry and biology possible follow from the quantization and conservation of orbital angular momentum. Every rotating thing in the universe is rotating for the same fundamental reason. Angular momentum is conserved and was imparted at some point in the history of that object. Every star, every planet, every galaxy, every spinning particle, every hurricane, every spiral galaxy arm, all rotating because angular momentum was given to them and has nowhere to go. The figure skater pulling in their arms and the Milky Way spinning at 220 kilometers per second at the Sun's radius are the same physics, angular momentum conservation, operating at completely different scales on the same universe. The tornado and the spiral galaxy are the same physics, rotating fluid in a gravitational field with Coriolis effects, operating at completely different scales in the same universe. The spin of an electron and the spin of a neutron star are both forms of angular momentum, one quantum mechanical and intrinsic, one astrophysical and kinematic, but both conserved by the same underlying principle. This universality of rotation is not a coincidence. It is a consequence of the symmetry of space under rotation, a symmetry that applies at all scales, in all situations, at all times in the history of the universe. As long as space has no preferred direction, angular momentum will be conserved. As long as angular momentum is conserved, things that start rotating will continue rotating. As long as things that start rotating continue rotating, and the universe contains density fluctuations that lead to tidal torques and gravitational collapse, everything that forms from rotating or tidally torqued material will spin, which is everything, which is why everything spins. The universe cannot be otherwise. A universe with the same laws of physics but without rotation would require a perfectly symmetric initial state, every density perturbation perfectly spherically symmetric, every tidal field perfectly isotropic, every quantum fluctuation exactly cancelling its neighbour. Quantum mechanics forbids this. Inflation spread quantum fluctuations that are non-zero. Gravity amplified them into the structures we see. Those structures are rotating because they could not form without angular momentum being imparted by the gravitational interactions of their asymmetric components. We live in a rotating universe, not in the sense that the universe as a whole rotates, but in the sense that everything in the universe rotates, because that is what the laws of physics and the initial conditions of the universe inevitably produce. The rotation is not incidental, it is structural. It is built into the universe at every level, from the spin of the electron to the precession of the cosmic filaments. Sit with that for a moment. The Earth is spinning right now, carrying you eastward at approximately 465 meters per second at the equator, the Coriolis effect of that spin shaping the weather systems that bring rain and wind and cloud. The Sun is spinning, its differential rotation stretching and amplifying magnetic field lines, driving the 11-year sunspot cycle that modulates the solar wind that shapes the space environment within the solar system. The Milky Way is spinning, carrying the Sun through one galactic orbit every 225 million years. The last time the Sun was here, the dinosaurs had not yet evolved. Distant galaxies, visible as faint smudges in deep images, are spinning. Disk galaxies, with stars orbiting their centers just as the Milky Way does. Elliptical galaxies, with stars moving in complex patterns that retain the memory of the mergers that formed them. All of this rotation, at every scale, in every direction, for every object, is the conserved angular momentum of the universe playing out across time. Imparted at the beginning by quantum fluctuations, redistributed by tidal forces, amplified by gravitational collapse, slowly transferred between objects by magnetic braking and tidal interactions, but never created, never destroyed, only moved. You are made of spinning things. Your atoms are spinning things, electrons in quantum spin states, nuclei in angular momentum eigenstates, the whole atom rotating in space. Your molecules are spinning things, tumbling in solution, vibrating and rotating in specific modes. The planet you live on is spinning. The star that lights your world is spinning. The galaxy that contains your star is spinning. The rotation connects you to the beginning, to the quantum fluctuations of the inflationary era that became the density perturbations, that became the tidal torques, that became the angular momenta, that became the spinning structures, that became the galaxy, that became the solar system, that became the Earth, that became the rotating atoms, that became you. Everything spins. And now you know why. There is a specific moment that can happen when you are standing outside on a clear night. Not looking at the stars, simply standing, feeling the ground under your feet, knowing in the way that knowledge is different from understanding, that the ground under your feet is moving, that the earth is rotating, that you are not stationary on a fixed surface, but are being carried eastward at roughly 465 meters per second, more than 1,600 kilometers per hour, by the rotation of a planet that has been spinning since it formed from a disk of gas and dust 4.6 billion years ago. You cannot feel it. The acceleration is too smooth, too constant, too long established for your nervous system to register. The rotation has been happening since before any life existed to feel it. But it is happening, right now, while you stand there. The ground beneath your feet is moving eastward at 465 meters per second. The atmosphere above you is moving with it, dragged along by friction and pressure, but not perfectly, and the imperfect dragging produces the winds and weather systems whose Coriolis-shaped rotations govern the rain that falls on the continent where you stand. The oceans are circulating in great gyres, driven by the same Coriolis effect. The magnetic field threading the space around you is generated by the rotation of liquid iron in the Earth's outer core, tens of thousands of kilometers below where you stand. The Sun, toward which you will turn as the Earth rotates, is also rotating, carrying its differential rotation that drags field lines, powers the solar wind, modulates the flux of cosmic rays reaching the upper atmosphere. That same solar wind flows outward through the entire solar system, carrying with it the memory of the Sun's rotation in the form of the Parker spiral, a spiral pattern in the interplanetary magnetic field traced by the rotating Sun's field lines stretched outward by the flowing wind. The solar system as a whole is rotating around the center of the Milky Way, completing one orbit every 225 million years, currently passing through the arm of the galaxy that will be called something else, if there is anyone to name it, in 200 million years. The Milky Way as a whole is rotating, 400 billion stars moving in complex orbits that together constitute the rotation of the galaxy. The local group, the small cluster of galaxies that includes the Milky Way and Andromeda, is itself rotating slowly, Andromeda and the Milky Way orbiting their common center of mass as they approach each other for a merger 4.5 billion years from now. All of this rotation, at every scale, from the quantum spin of the electrons in your atoms to the orbital angular momentum of the galaxy, is the same quantity: angular momentum. Conserved because space has no preferred direction. Imparted originally by the asymmetries of the early universe, quantum fluctuations stretched to cosmic scales by inflation, grown by gravity into density perturbations, twisted by tidal interactions into the angular momenta of forming structures. Nothing created it. It was always there, always present in the quantum fluctuations, always ready to be amplified by collapse, always conserved by the symmetry of space. The rotation of everything in the universe is not something that happened to the universe. It is something that the universe is, a consequence of its quantum mechanical origin, its symmetrical laws, and the gravitational amplification that takes small asymmetries and makes them large. The law that governs all of this, the conservation of angular momentum, is not an empirical fact discovered by measuring spinning things. It is a theorem, a mathematical consequence of a symmetry of space. If space has no preferred direction, if the laws of physics are the same regardless of which way you point, then angular momentum is conserved. This was proved by Emmy Noether in 1915 in one of the most important mathematical results in the history of physics. The symmetry implies the conservation. The conservation implies that anything that spins will continue spinning until its angular momentum is transferred somewhere else. The universe has been transferring angular momentum around for 13.8 billion years. Stars have transferred angular momentum to planets through the protoplanetary disk. The Earth has transferred angular momentum to the Moon through tidal friction. The Moon is receding. The Earth is slowing. The angular momentum of the Earth's spin is becoming the angular momentum of the Moon's orbit. Binary stars transfer angular momentum between each other through mass transfer. Galaxies transfer angular momentum through tidal interactions and mergers. Black holes radiate angular momentum in gravitational waves as they spiral together. But none of it disappears. Every transfer is exact. Every conservation is perfect. The angular momentum that started in the quantum fluctuations of inflation is still present in the universe today, redistributed across every spinning object, every orbiting body, every rotating quantum particle. but conserved in total to whatever precision the most accurate measurements can achieve. You are part of this, not metaphorically, physically. The angular momentum of the atoms in your body is part of the total angular momentum budget of the universe. The quantum spin of every electron in your body is a tiny contribution to the total. The thermal rotation of every molecule is a tiny contribution. The revolution of your body around the Earth's axis as the planet spins, and around the Sun as the Earth orbits, and around the galactic center as the Sun orbits the galaxy, all of these contribute angular momenta to the cosmic total. You are a spinning thing in a universe of spinning things, made of spinning particles. Moving through space in circular and elliptical and spiral paths that are all expressions of conserved angular momentum. The rotation is not something external to you that you observe from outside. You are inside it. You are part of it. You are constituted by it. The quantum spin of the electrons in your atoms determines the chemical properties of those atoms and, through chemistry, the structure of the molecules that make you up. The orbital angular momenta of those electrons determine the shapes of the atomic orbitals, and through those shapes, the geometry of the chemical bonds, and through that geometry, the three-dimensional structure of the proteins and DNA and membranes that constitute your biology. The Pauli exclusion principle, which follows from the half-integer spin of electrons, is what prevents the atoms in your body from collapsing into each other. You are held in your current form by quantum angular momentum. The rotation of the Earth shapes the climate you evolved in, the Coriolis effect that organizes weather, the precession of the rotation axis that drives the Milankovitch cycles, the tidal breaking that has been slowly lengthening the day for billions of years. The specific length of the day, 24 hours, is not arbitrary. It is the current value of an Earth rotation that was much faster when the planet formed and has been slowing ever since. The biology that evolved on this planet, including you, evolved in a 24-hour light-dark cycle that is written into your circadian rhythms, your sleep architecture, your hormonal cycles. The rotation of the galaxy determined which part of the Milky Way your solar system has passed through over its 4.6 billion-year history. Which star-forming regions, which spiral arms, which regions of denser interstellar medium that might have compressed the heliosphere and increased cosmic ray exposure. The specific orbital history of the Sun through the galaxy is part of the environmental context in which life evolved on Earth. All the way down to the quantum spin of your electrons, all the way up to the galactic orbit of your solar system. Rotation at every scale, conserved at every scale, inherited from the same source, the quantum asymmetries of the inflationary universe, and expressed differently at every level, but governed by the same law. The universe spins because it began with angular momentum it cannot lose in a space whose symmetry ensures it can never lose it. Every spinning thing is carrying the memory of the rotation that was imparted to it, from the gas cloud that formed the solar system, from the tidal torques that set the proto-galactic halo rotating, from the primordial density fluctuations that were not perfectly symmetric, from the quantum fluctuations of the inflationary era that made perfect symmetry impossible. The spinning top on a table will eventually fall. Friction with the table transfers its angular momentum to the Earth, and the top stops. But the angular momentum does not disappear. It is added to the Earth's total, infinitesimally changing the length of the day, transferred into the angular momentum budget of the Earth-Moon system. Even the falling top is conserved. Everything spins. The universe has been spinning for 13.8 billion years and will continue spinning for as long as the laws of physics hold and space maintains its rotational symmetry. The rotation is not a feature of the universe, it is the universe, the expression at every scale of the symmetry that makes angular momentum conserved, and the quantum mechanics that ensures the initial angular momentum is never zero. You are standing on a spinning planet, orbiting a spinning star, in a spinning galaxy, in a universe that, while perhaps not rotating as a whole, has angular momentum distributed through every structure within it, conserved forever by the symmetry of the space through which everything moves. Feel the ground move. It is moving, right now, carrying you eastward at 465 meters per second, as it has for 4.6 billion years, as it will for billions more. That motion is the universe being what it is,